we are continuing further to the lasso procedure, there are some heuristics that we can bring in. So, instead of fixing the L1 norm to be less than or equal to t, we can say that the L1 norm has to be less than or equal to t plus some epsilon, where epsilon is a positive quantity. And by folding this constraint, we may shrink this further, which means we may accelerate towards our solution, right. So, let me write this formally. So, instead of testing if the L1 norm of the weight vector is less than or equal to t, we can introduce a quantity epsilon greater than 0 such that we consider the L1 norm of W to be less than t plus epsilon. So, at every iteration this norm shrinks and hopefully we land up with the solution. Now, there are two important things that we need to know. The solution from a previous iteration where I had a certain constraint, a certain set of constraints, may not be suited to the present constraint. And this implies that one needs to optimize again, because the initial condition from the previous step or the terminal condition from the previous step may not be a good initial condition at this step. Okay. And the second thing is adding the sign constraints can have swings in the variables, right. So, adding the sign constraints can have variables that can have large swings from something which is highly positive to something which is highly negative, and these issues can be pronounced when we particularly deal with correlated variables. So, therefore, this is another consideration here. Now, we can introduce non-negative variables. So, because the weights themselves can be positive or negative, but if we were to make them all non-negative, then I need to bring in two other variables, both of which are positive, that I can express this variable as a difference of these two non-negative variables. So, let us see how that can be done, and that leads into doubling the number of variables, but that can help us arrive at a more compact form of the linear constraints in terms of the weights. Okay. So, we introduce non-negative variables as follows. The idea is to express each Wi as a difference of two non-negative variables. So, what I have here is Wi is expressed as Wi plus minus Wi minus, and both Wi plus and Wi minus, both of these are non-negative, that is they are greater than or equal to 0. Now, if Wi is greater than 0, then I choose Wi plus to be equal to Wi and Wi minus to be 0. Likewise, if Wi is negative, then I choose Wi plus to be equal to 0 and Wi minus to be equal to Wi, and the last case is Wi plus equals Wi minus equals 0 if Wi equals 0. So, we have these three cases. Now, you can imagine for k variables in the weight vector W, we introduce 2k non-negative variables. And therefore, in some sense we bring in degeneracy in the number of constraints, right. This implies introducing degeneracy we bring in degeneracy in the constraints. So, for example, if we consider a 2 variable case, we have W1 plus is greater than or equal to 0, W1 minus is greater than or equal to 0, W2 plus is greater than or equal to 0, W2 minus is greater than or equal to 0, and then summa I equals 1 to 2 Wi plus Wi minus, this is less than or equal to t, right. We just have a linear constraint and that is degenerate. So, these are some techniques where we can simplify our problem further, but the consequence is we bring in additional variables and then we will have to consider this in our optimization problem. Now, there are techniques such as grafting, where there is a focus on the unconstrained problem formulation, where we need to decide how to choose the weights and how they should be adjusted away from the 0 set in order to decrease the optimization criterion by maximum amount. I have the 0 set, that means my variables are 0 there, and I have a free set where it is I look at the optimization there, right. Now, in the 0 set I want to look into those variables that I can move the variables to the free set, and how should I decide what variable has to be moved iteratively, right. And that leads into this concept of grafting. It is a very interesting idea, that is I take at every step I pull out a variable from the 0 set and push it into the free set, and in the process I want to optimize my objective by maximum amount. That's the key idea. And particularly in the context of deep learning, people have been looking into these techniques. So let me introduce this idea to you. This idea is called grafting. And it was originally due to Perkins and the co-authors, and it appeared in the Journal on Machine Learning Research in 2003. So I will give you the basic idea. So we incrementally build a subset of parameters that are allowed to differ from these zeros, and how this is done is through a meta heuristic. So at each iteration we use a fast gradient meta heuristic to decide which zero weight should be adjusted away from 0 to decrease, this is very important, to decrease the optimization criterion by maximum amount. So basically from the 0 set we want to put the variables to the free set, and how we choose is based on a heuristic. So let us set this up and see what it is. So recall that we were looking into this constraint x w minus y, this normed square subject to the L1 constraints on the weight. So if we take the gradient with respect to the weight using straightforward matrix calculus, we get it to be as follows. Now for variables that are 0, which is wi equal to 0, so we do the following: sine of wi equals 1 if xi transposed y minus x w is greater than lambda. That is, we look at the ith data point here, which is and which we which is a 1 by n, and then we multiply this by y minus x w. Okay. Now by convention if xi transposed y minus x w equals lambda, then the gradient is set to 0, right. So, this is how we adjust. So, I think what we have to pay attention here is the xi here corresponds to the ith data point, that is the attribute I over all the data points, right. It is the attribute I over all the data points. From this we can evolve a procedure So, we have a condition. So, at every iteration we test if this inequality is satisfied for each I, right. So, if condition I call this condition A, if condition A is false, then the variable whose derivative has the largest magnitude is added to the free set. That is, we consider, so I think I should make a note here, we consider all variables in the 0 set initially, is an important thing. Then at each iteration we test if this condition is met, and if the condition is false, then the variable whose derivative has the largest magnitude is added to the free set, and subsequently any popular method such as quasi-Newton method or the Broyden-Fletcher Goldfarb-Shannon, it is also called BFGS algorithm. So, any popular method can be used to optimize the variables in the free set. So, the free set is recomputed after every quasi-Newton iteration, and you land up with and it terminates with a set of non-zero variables and 0 valued variables with the largest absolute value in magnitude of the derivative, right. You look at the derivative and figure out the variable whose derivative has the largest magnitude, and then you add it into the free set. And this is the grafting idea, and this also works pretty well in practice. So, the idea is as follows: we consider all variables in the 0 set, because we have to peel and pull the variables from the 0 set to the free set, over which you have to do your optimization, right. You start with the variables in the 0 set, which are all those wi's that are 0, then you check if this condition is met, right, and then if the condition is false, then the variable whose derivative has the largest magnitude, you pull that variable out and put that into the free set, and then over that set you optimize using any technique that you are familiar with, like quasi-Newton, etc. Okay, and this procedure is repeated till you peel the variables or pull the variables out from the 0 set to the free set. So, one can study the convergence properties of these algorithms, investigate into stability and all the properties that you think about the solution to the problem as such. And I would not delve into these details because this is part of an optimization course, but I just wanted to touch upon some basics of L1 regularization, L1 regularity constraints, and some basic problems with L1 constrained and unconstrained optimization setup and algorithms towards these, so that we can better appreciate what is happening when we actually deal with these real problems where we bring in sparsity constraints. And a great detail of L1 regularization theory can be a course in itself, because we have a vast variety of techniques till date, and I would leave this possibly as a topic for a future course. Okay. So, with this we cover the basics of L1 regularization, and hopefully you will find these techniques useful for your applications in practice.